Hey guys, today we're going to be looking at 5.2. I'm going to go through most of this. I'm going to draw a couple of diagrams, but I went ahead and wrote the definitions of all these vocabulary words because I didn't want you to have a video of me writing definitions. So if you need to pause it and fill this out, you can, or fill it out as we go. You're more than welcome to do that as well. So it says to define the following words, draw diagrams to support your definitions. And let's start with the vertex. So the vertex is two non-collinear rays that form an angle by sharing an endpoint called a vertex. So the vertex is going to be this endpoint here. This is the angle that they create. The initial side is the starting position of the ray, and that's going to be this bottom one here. The initial, and then the terminal side is the ray's position after rotation. So this is going to be the terminal side. And I guess I'll write side here as well. All right, a standard position is an angle with its vertex at the origin and initial side on the positive x-axis. All right, so let's give an example of something like this. All right, it has positive x-axis, and it's creating a vertex at the origin up. The initial side is the x-axis here. All right, and then its terminal side is somewhere over here. Just an example. And we'll go ahead and label this standard. All right, positive angle is an angle created by counterclockwise rotation. Okay, and counterclockwise is going to be this direction. So I'm just going to label that positive here. And then negative angles are going to be generated by clockwise rotation. And this is always going to be starting at the x-axis. So going negative goes this way. And you can think of it in accordance with the y-axis. If it's using, if it's going towards like negative y, it's going to be negative. And then as we come up, this is getting into positive y values. This is the positive direction. All right. What is radian measure and why can't we just always use degrees? Well, we can't always use degrees because a degree has no relationship to linear measure. The radian measure the measure in radians, which is the radian measure, of a central angle of a circle is equal to the ratio of the length of the intercepted arc and the radius. All right, and I'm just going to hold this here for a second so you can write some things down. And I don't think there's anything for me to draw for that one. So what are the conversion rules for converting degrees to radians or the reverse? Because sometimes you will be asked to convert something to degrees or to convert it to radians. So this is where we have degrees to radians. You'll multiply by pi times the radians divided by 180 degrees. And then if you're going from radians to degrees, you're taking 180 degrees and dividing it by pi times the radians. All right. What are coterminal angles? Describe what you would do mathematically to find a coterminal angle in both radians and degrees. All right, because of rotations, two angles can have the same initial and coterminal sides, but different measures. These are called coterminal angles, and we'll eventually draw a picture of this, but for now, these are just definitions for you guys. So as we go through 5.2, past this page, onto others, you'll get pictures and definitions as we go, examples of everything, which will help a lot. All right, you can either add or subtract by a multiple of 360 or 2 pi radians, which, again, we will do all that later on in 5.2. And then what is the formula for finding arc length? Doesn't matter whether the angle is measured in degrees or radians to use this formula. If the radian measure is a central angle in a circle with the radius r, the length of the intercepted arc is radius times the degree measure in radians, where this symbol is measured in radians, of course, which we've just gone over. And again, these are just definitions, and we're going to go over a couple of examples as we go. So it says to define linear speed and angular speed. Linear speed is the rate at which an object moves along a circular path, and then angular speed is the rate at which an object rotates around a fixed point. All right. What is a sector of a circle? What formula will find the area of the sector? All right, a sector is a region bounded by a central angle and its intercepted arcs. So I've gone ahead and drawn an example of a sector. Basically, it's going to be like a section. All right, and then we would find the area by doing 1/2 times the radius squared times the measure in radians of that angle. All right, we're going to fill in the table based on special right triangles. I went ahead and drew the 45, 45, 90, the 30, 60, 90 triangles in the length of their sides. And then I've got the SOHCAHTOA as well as the cosecant, secant, and cotangent here, and that's going to help us. This is going to be pretty broad of a graph, kind of going over each of these things. So sine of 30, which is opposite over hypotenuse, if we go to 30, opposite is x, hypotenuse is 2x. So it would be x over 2x, simplified is going to be 1 over 2. All right, 45 degrees, which is going to be opposite over hypotenuse, x over x times the square root of 2 gives me 1 over the square root of 2. And of course, we need to get rid of the square roots in the denominator. So once we do that, we would end up with the square root of 2 over 2. All right. Again, opposite over hypotenuse for 60 degrees. Opposite, x times square root of 3 over hypotenuse is 2x. So we have x to the square root of 3 over 2x. We'll be able to get rid of those, and then we will just have the square root of 3 over 2. All right, cosine. Now we're looking for adjacent over hypotenuse. Cosine for 30. Adjacent is going to be x times the square root of 3 over hypotenuse, which is 2x. And again, we'll cancel those out, and we will get the square root of 3 over 2. All right, adjacent over hypotenuse for 45, adjacent x. And it's going to be the same here as it was for this one. Because our adjacents are both going to be just x, that's going to end, of course, being square root of 2 over 2. All right, adjacent over hypotenuse for 60. Adjacent x over 2x, which again leaves us with just 1/2. All right, tangent, opposite over adjacent, 30. Opposite over adjacent, so x over x times the square root of 3, which is just 1 over the square root of 3. If we were to rationalize this and multiply both by the square root of 3, we would end up with the square root of 3 over 3. All right, tangent, opposite over adjacent for 45 degrees. Opposite is x over adjacent is x, x over x, which is equal to 1. All right, and then we have for 60 degrees, opposite over adjacent, x to the square root of 3 over x leaves us is equal to just the square root of 3. All right, cosecant, which means we do the reciprocals of SOHCAHTOA. So I took opposite over the hypotenuse and I flipped it, and I flipped cosine for secant, and then I flipped tangent for cotangent. So we're basically going to take everything here and flip it. So if we were to take sine 1 over 2 and flip it, we would just get 2. All right, for this one here, we would get let's see, 2 over the square root of 2. 2 over the square root of 2. If we rationalize, we would end up with 2 square roots of 2 over 2, which gives us just the square root of 2. So at this point, all we really have to do is take each of the answers that we got and flip them. So then here we have 2 over the square root of 3. If we rationalize, we would end up with 2 square roots of 3 over 3. All right, same thing here, 2 over the square root of 3, and we get the same thing, 2 square roots of 3 over 3. We're going to take this one and flip it, so 2 over the square root of 2. We've done that up here as well, so we'll end up again with the square root of 2. And then 2x over x, well, 1/2, which is going to be 2. All right, and then here we would have 3 over the square root of 3. If we rationalize, we would get 3 to the square roots of 3 over 3. Cancel that out, we would just get square root of 3. All right, here we have 1 over 1, which is just going to be flipped and still be 1 over 1. And then technically here we would have 1 over the square root of 3 because we have square root of 3. And then to rationalize, we would end up getting the square root of 3 over 3. All right, think about it. A and B are acute angles of a right triangle, and where the angle of A is less than the angle of B. So I went ahead and did an example here. I mean, you could have done 30 and 60, but I just went ahead and did an example. And these I just plugged into the calculator. So I plugged in sine of 40 and sine of 50. You could have technically just used this chart, but I wanted to just plug in examples and see. And I found that sine of A was greater than sine of B, so this is false. And again, I just took 2 examples of numbers that are acute, aka less than 90 degrees, where A was less than B, and I plugged them into the calculator. So I took cosine of 40, cosine of 50, and I found that cosine of 50 was, in fact, greater. True. And then a tangent of 40, tangent of 50. And again, I found that the tangent of 50 was greater. So the first one is false, and the other 2 are true.